commercial vehicle test track here in Eversen. I think you will get later on quite a good impression of what we have here, the asset we have here. My name is Ivan. I met some of you yesterday already. I'm leading the research and development in the commercial vehicle division. I want to spare you my profile here. You can look it up in LinkedIn if of interest. Just want to mention I joined ZF back in 2015 as part of WAPCO, and roughly 1.5 years ago I took over from Dr. Christian Brajdic in my current role. Let's look on the agenda. So I would like to guide you through some of the key technology trends we see today, their implications, and how we as a ZF, as commercial vehicle division, are approaching them and tackling them. And there is, I would say, a huge bandwidth of challenges where I believe we as ZF are very well prepared with our capabilities to tackle them. And specifically, you see a chapter here about software-defined commercial vehicle. It's by purpose that I call this software-defined commercial vehicle, because I believe there is quite a significant difference what we see in the pass car area with a software-defined vehicle. First of all, and second of all, I want to deep dive into this, because I think we see in pass car a lot of hype that is somehow translating now into a hype of commercial vehicles, but the translation into the reality will not be a hype. It will be rather a considerate approach, trying to move along what is the best balance between invest and return. So we will deep dive on this a little bit more, and then later on I will give you an overview how your life experience will look like here. Let me jump over that. To start off, short overview, short impression of our test track here in Eversen. I'm not sure if anyone was here before. We founded it back in 1993. You see here the inner circle, the inner ring. So it was rather maybe a smaller test track back then. And since then we had 2 times an extension, one in 2009 with the dynamic area you see there in the middle, and in 2020 another extension with the outer ring, which now is enabling us for various use cases in the area of ADAS and in the area of autonomous driving. Basically, we can drive with 90 kph around the outer circle without having our acceleration sensor kicking in, so you can basically continuously drive, which is an important use case also for autonomous driving. It is actually a unique differentiator for us as a tier 1 supplier in the commercial vehicle industry. We are owning the test track, and you see here we are basically equipped fully with infrastructure, whatever is required to drive daily testing, validation, development of commercial vehicles. We have our own fleet. We have workshops here, various workshops, offices, 80 engineers on site, etc., etc. It's fully equipped. You will get an impression later. And I also want to provide an overview of our research and development organization in CVS. So we are, you see, a true, I would call it a true global organization with 40 locations worldwide, and in all major regions we have a very strong footprint with strong local capabilities, and with this we have also quite a deep market understanding. And that's important for us, especially because we are developing a lot of global platforms. We want to scale them into the regions, and you can imagine how important it is to understand what in a specific market is required. Now let's move to the technology trends. You might recall a couple of years ago the big trends, ACE. What we summarized, we called it ACE: automated, connected, electrified. And that's still there. It's we are still following that path, but you see here an indication in the graphics. We see a more and more interweaving of these trends, of these domains. And let me go to the next slide. So what we see is that ACE will not be a domain-by-domain approach for the future. There will be an intermeshing in terms of technology, and these domains will increasingly interconnect, interweave with each other, mesh with each other, and on top, those domains or trends are getting fueled by new technology streams, by an advancing technology base. And I also have to say, we as a ZF, we are kind of driving this advanced technology base. So, for example, you see here on the slide, by an extension of, or by extending the digital move to a digital ecosystem, which not only covers the product itself, but the product in operation across the complete life cycle, we see that we can maximize operational efficiency. Or in the integrated system solutions, by moving from isolated views, from isolated intelligence of the systems to a combined intelligence, we can maximize safety and performance. In the electrification area, we see that there are different paths to achieve a decarbonization and to later on reach the electrified future. And we believe we can support the transition to this future by offering multiple options, like for example the trucks on hybrid. So, and last but not least, you see here a kind of an underlying technology evolution of vehicle architectures that is related to software-defined vehicle. And this is kind of intermeshing with all of this together. And it's actually a huge opportunity, all of this, to combine it and to interweave it in the right way to add more value to the CV of the future. Now, on the one hand, we see this turning and converging technology streams, creating opportunities for additional value. But on the other hand, we have a great deal, I would say, of diversification across the globe. And especially across the different regions, how they approach product development, how they approach regulations. Let's look on the middle part. I put in here some regulatory, some qualitative statements about how the regions are approaching regulations across different domains like emissions, ADAS, automation, safety, but also in the digital ecosystem, especially cybersecurity, we see different approaches in the different regions. So it's actually putting us on a challenge how we can offer products, how we can develop products and offer products in all regions that are fulfilling all these regulations while keeping on our side a reasonable investment level. When you look on the top part of the slide, I tried also to cover with a qualitative statement what the different regional drivers are. We see in the different regions there are different approaches to product development and to market development. Let's look on China, very prominent now. There is a high focus on speed and scale. While in Europe, you see a high focus on compliance, on regulations, but also on platforms and ecosystems. In USA, we see rather a refocusing of the technology direction, maybe more focus on classical technologies. And in India, we just discussed high focus on growth, but on best cost levels. And Japan and Korea, Brazil, South America, they are again trying to find their own paths. I mean, of course, everyone is looking to the other one, But at the end, what we end up with is a very diversified picture. So we, as a tier 1 supplier in industry, we have to accommodate this complete bandwidth of diversification, while at the same time we try to fuel the converging of the technologies. So how do we do that? So switching perspective, we have already a strong foundation with the broadest portfolio across all relevant vehicle categories: trucks, trailers, buses. So not only we can go deep into a specific system with our system expertise, we can also go across the vehicle and also across the different vehicle variants. You see here the different vehicle categories. So these are the best conditions, not only to combine intelligence of the different systems, but also to push for product ecosystems across the different vehicle categories and supporting the evolution towards a software-defined architecture, software-defined future. So, rough overview. Now let us look on how we translate this into a kind of a timeline. First, the basics, the fundamental enablers you see here. So these are the absolute precondition for any further technology evolution, and we already implanted this into the genes of each of our products accordingly. System scalability, adaptability, I think it's clear. I mentioned it, we need to make sure that whatever we develop as a global platform can be easily scalable across different vehicle variants, across different customers and across different markets. Regulation compliance is absolutely basics, I would say. But also we need to ensure that for our customers we can achieve investment sustainability. And for the end customers, for the fleets, a reasonable total cost of ownership. Now, in the area of automation, we have prepared our recently launched technologies and platforms already for the next step towards software-defined commercial vehicle. So, for example, we can easily extend our MBSP braking system to a capability for autonomous driving level 4. So we have a base system, and that's what I mean with scalability. With, I would not say a little more effort, but with a reasonable effort, we can extend it as a base system for a level 4 truck. Or you see here our ADAS platform that can be easily adapted to various markets, to various customers, has a high degree of flexibility and configuration, but it's also built in a way that we can develop local solutions in certain markets. Like, for example, in China, we have reused components of our current ADAS system to develop a completely local solution, completely with our local team. And then I just want to mention another example, our IBP, Intelligent Braking Platform for trailers. So we are also developing and delivering braking systems for trailers. So this is already considering a fusion of different functionality beyond braking. So, for example, we are offering this braking system in a variant which includes the suspension functionality. Now let's move on to the field of electrification. And here I would say, I would put it a little bit different. We are extending our portfolio of technologies to accommodate basically different degrees, different speeds of adoption of electrification in different markets. Now, the USA is following their different approach, a different speed maybe than China. That means we are adding a SCOL technology here for air supply, which has a high modularity in terms of customer application use case. We are adding trucks on hybrid. We had a discussion before, trucks on hybrid technology, which we see as a bridge technology to the direction of decarbonization. So here it's more extending portfolio and increasing the scalability of our products. And last but not least, the area of digital. Here we have established the basics. There have been a couple of regulation updates in the last months, years across the different regions. One is cybersecurity, public key infrastructure. The other one is software update management. So these basics are fixed, and this is actually the building step or the base step to evolve now quickly building digital ecosystems around our products. That's the basement. Last but not least, I want to highlight two examples that are demonstrating two of our key capabilities in ZF to support this continuous technical transformation. You see here in the bottom middle part, I call it a braking and e-drive synergy program. And another example I want to bring, you see here our C-tracks, our X-tracks as a picture to explain how we have approached developing this global scalable platform. So I brought two videos. And on the left side, you see, I would say, a state of the art solution across the industry for a lift-off scenario. Let's look shortly on it. So, driver accelerating, you see the slip, which is normal. System is controlling, braking down a little bit and ensuring that the vehicle can lift off. State of the art. Where could you improve? What do you think? Can this be improved? Looks like, but it's state of the art. Let's look on the second video shortly. The time for liftoff, almost the same, basically the same. But have you detected any slip?
No.
There is no slip. So how did we achieve that? And that's by, we are responsible for braking and e-drive. We develop both systems. So we try to push the limits, going to the border of the system control by combining the control intelligence of both systems. And by doing this, we have reduced the latency times for the control of the system dramatically. And it's all about latency times. And this can only be done by a company like us who is developing both systems and has the deep expertise in both systems. Because at the end, of course, that's this lift-off scenario. Now imagine the other way around. Braking scenarios, recuperation scenarios, operation scenarios, where we can increase now the efficiency, turn it around, the efficiency of our e-drive significantly. The second example I mentioned before, global scalable platforms. Let's look on the bottom of the slide. You see here 5 different, let's call it, in applications or integrated applications for our e-drive. We have the axle integrated e-drive in 2 variants, let me call it performance variants. We have the central drive in 2 variants, and we have an axle integrated drive, especially for low flow buses. They have a different requirement in terms of packaging for the low flow buses. And all of these variants we can apply in all different kind of vehicles across all markets and different customers by a base fundament of 5 different components you see here. So the e-motor, inverter, the transmission, e-actuation and electronics and control are basically the same. They're just configured and integrated differently. So this enables us to quickly adapt to market needs. and deliver solutions for our customers for their specific use cases. So, 2 examples of 2 different kind of capabilities, but which I believe make us unique, and as what I said, help us fuel actually the technical transformation we see out there. Now, software-defined commercial vehicle. As I mentioned, it's an underlying stream of transformation we see out there, but affecting the complete vehicle architecture. Now, I thought I bring a vivid use case to you. Why actually should we do SDV or SDCV? I just imagined and tried to picture the future CV ecosystem. Now you have a vehicle operating, and of course, out of all the sensors on the vehicle, collecting data all the time. Now imagine this vehicle is continuously connected to a cloud. So you could continuously transmit data to the cloud. You could already do a first level processing on a vehicle. You could try to detect unusual sensor values, for example, and then give a hint, okay, here I have an area of unusual data, have a look later on this. Now in the cloud, you are processing it. And in the cloud, you could check the function behind the data. Let's assume it's a braking maneuver that has produced some unusual data, and you could detect, is there a deviation from what we would expect a braking in a certain maneuver in a certain use case actually to perform. If so, you could analyze the deviation, where it comes from, root cause. You could develop a fix, an improvement. Out of all the vehicle data, you could create a simulated test environment. You could test the improved function in this simulated test environment. You could create out of it a new software, and then, download the software to the vehicle. You could even say, we just download it to a limited number of vehicles to pre-test it in the field, and later on you roll it out to the complete fleet. It's just one use case. Okay? And now imagine you equip this cycle with a lot of automated processes, maybe with the help of AI. So in extreme case, maybe there is not even a human being involved, except maybe at the end to sign it off. How quickly could this cycle happen? In extreme case, I don't want to make any commitments here, but you can imagine it's maybe a matter of days or even a matter of hours. While today, if you want to change a software and improve a software, it's a long cycle to bring it into the field. Yeah? And now let me even go one step further. Now there is out there a new term, AI-defined vehicle. So what actually does it mean? Now imagine you have an AI, let me call it like this, an AI function on the vehicle. And that AI function could screen and analyze the driver behavior and detects that the driver always on a certain route at a certain point lifts the axle because there is maybe a sharp curve or whatsoever. Then the AI concludes, maybe we can do this automatically, transmits the data to the cloud, proposes to change or to improve a function, or maybe to introduce a new function. And then you go all the cycle again. The only difference is this improvement comes from the AI, from the vehicle. The vehicle is improving itself. That's what I would call an AI-defined vehicle. Now, I will come to AI later on with a slide. There is a notion out there that AI-defined vehicle will replace software-defined vehicle. I don't believe that, because I think the step of software-defined commercial vehicle is actually fueling this evolution towards AI, because the base for having an AI functioning as expected is data. And for software-defined commercial vehicle, a crucial point is it's not about software. Software-defined vehicle doesn't mean software. It means connecting all the ecosystem together. That means for a software-defined commercial vehicle, you need to tackle the mechatronics layer, the actuation layer, architecture, the, let's call it integration layer architecture with different electronics, the software layer architecture, the functional layer architecture, and the cloud architecture. Everything needs to work together seamlessly in an ecosystem. And once you have that, then you have very good foundation to go towards AI-defined vehicle. Now, important to mention, and I think I mentioned it before, I believe there is a fundamental difference between software-defined architectures and approaches in passenger car versus commercial vehicles. And I put it very simple. I don't want to be disrespectful, but a passenger car basically is a box with 4 wheels. That's it. Now look on commercial vehicles. You have rigid trucks, you have trucks with trailers, you have buses, and you have all different kind of special applications. You have off-highway applications and so on, and they all have different use cases. And you need to make sure you cannot pack in a software-defined approach. You cannot pack all of these potential variants in your base solution, because then all variants will be too expensive. You need a scalable solution. In PASCAR, it's a different one. You don't have so many variants, so you can pack everything in. You have different volumes. Here, let's go through some of the points. The second point, you have a low number of architecture variants, but a high volume behind. So rather a quick return, a quick payback, while in commercial vehicles you have huge variants of different vehicle types and low quantities. Yeah? In PASCAR, it's more about the end user experience, digital lifestyle, all this kind of stuff, while in commercial vehicles, I tell you, it's all about operational cost. And if I go to a customer and present them, hey, let's go together towards a software-defined vehicle, he's asking me, that costs a hell of money. When is the payback? What is the value I bring here? Now, not in 5 years. So that means we need to approach it differently. We need to think about whatever step we take, how can we actually create a payback? Best would be in 1 year, but latest in 2 years. That's the question we have here. A couple of other points you see here, but as a conclusion, there are different environment and requirement between PASCARs and commercial vehicles that will lead to different approaches. And I personally believe in commercial vehicles it will be a stepwise approach, always along the balance of invest versus return. So, what kind of transition we see? So on the left side, it's more state-of-the-art where we are today. It's a distributed electronic architecture with embedded software on it. And yeah, I would say all of them have a little bit different architecture. It's not a harmonized ecosystem, I would call it. And nevertheless, we expect this kind of architectures will be out there at least until 2030, but honestly, if you ask me, 2035 still, and maybe even a couple of years more. At the end, the target picture, I expect first of these coming up from 2033 is kind of a fusion, a clustered architecture with maybe 2 or 3 central computing units. Computing means on a higher performance level than what we have today. Also, I believe that in that range in time, we will see that highly safety critical systems will somehow also get integrated in this computational architecture. which I don't see before. And what is happening in between? And that's now the important part. That's the path along the practical implementation that I just described. There will be quite a variance of different coexisting architecture approaches across the different systems. You will have legacy systems with a state-of-the-art architecture, while still trying to combine in a different other system with a high-performance computing architecture. Now you need to make sure, we need to make sure as a supplier that this works together. And each customer will approach it differently. The one customer wants to move in system A to a computing architecture, the other customer in a system B, or maybe combine it in different variants together. So it will be quite a challenging approach, but especially here, I think because we are covering all the system portfolio you can imagine in a commercial vehicle, we have all the capabilities on board to exactly support this kind of a flexibility. So let's get a little bit practical. I would like to guide you through a thinking experiment. You see here, I pictured a little bit the theory, the target picture. We have it's quite simplified, I have to say, but nevertheless it helps to think about it. We have a mechatronics layer architecture. We have an integration layer where you can already kind of consolidate sensor data, communication data into zone electronics. And then finally you have the computation layer with a high performance computing unit where then different systems are consolidated. This unit is connected to a cloud. So, as I mentioned, each of them has their own architecture, but harmonized with the architectures of the other layer. Now, do you believe that this will come overnight? We have vehicles out there, we have customers invested in current systems running out there. Normally, I would say the commercial, let me call it commercial life of a product is at least 8 years in commercial vehicle industry. In test car it's different, but you need to make sure that whatever you invest with all the lower volumes behind them in test car, you can still get your payback. So if you introduce a system, you cannot change it again after 3 years. No? So you have kind of a legacy as OEM, as vehicle manufacturer, and also we as a tier 1 supplier, which you need to consider here. So it will not come overnight. How will it come? Let's look on the reality. And I pre-populated the reality already a bit. So let's imagine a starting scenario. Some of the vehicle systems might already be on a future architecture level, like some zone input-output electronics, some of the sensors, some of the actuators, and maybe also the connectivity module, and all the other ones in gray are still more in a state-of-the-art level. And if you think about it, how now, if you are an OEM, how would you approach this? Where would you introduce a high-performance computing unit? And what I believe, that it will come first on those systems that anyway will need that high performance in the next step. And which system is it? It's ADAS. Because you need to process all the sensor data. You have radar. Maybe you have several radars around the vehicle. You have camera. Maybe you have lots of cameras around the vehicle. A huge amount of visual data, of radar data, of point clouds. You need to process that. You need to detect the objects in this data. You need to fuse all this data. So it requires anyway high performance. So even if we would not go towards a software-defined architecture, I think this system will need to move over to a high-performance computing unit. So that would be a starting point. And it's still the best balance between what you require technologically, what you invest in, and what you get as a return. Now, if you are there, you could say, okay, now I have a performance computing already. Could I extend this? not introduce a second one, but use the existing one. So you could extend this to the cockpit or HMI. Why? Because in the HMI you have also a lot of graphical and visual data. Yeah, maybe you have images of certain cameras being routed to the HMI or any kind of additional information. Yeah, so that could be a potential next step. And once you are there, you could also say, okay, maybe it makes sense to, depending on the performance level of the computing unit, to take the complete HMI into it and maybe even add connectivity to it. That's a theoretical scenario because in terms of connectivity, different regions have different restrictions. So you cannot use the same connectivity module in all the countries. In some countries, you need to use local suppliers. So it could be a scenario where you cover those regions where by requirement and by regulation you can use one connectivity unit, but maybe not in those where you need to cover other ones. There you need the flexibility on the connectivity unit. And then you can say, okay, maybe we can integrate more vehicle functions into it. For example, some customers, they have vehicle control modules and so on, where they control certain vehicle functions, vehicle level functions. Let's integrate this here into a computing unit and maybe also separate it from the HMI. And finally, and I flip over, you see here the legacy domains. In a final step over the years, you could put maybe remaining legacy functions also into a computing unit. And last but not least, I don't have it here, you see there on the right side the safety critical domains, which for example is braking. So at the moment, I would say there is a lot of respect on our side, but also in the industry, in bringing an embedded safety critical system like a braking into a computing unit. It's a hell of an effort, complexity, because in these systems you have, how can I say, very deeply implanted functional safety concept between different functions, messages and so on. And to bring this into a computing unit, you need to break it up and assemble it again. And there is a lot of respect. So therefore, I think in the near future, we will not see this. Maybe the one or other also startup might try it. I just say we have a lot of respect about it. So that's the end of my thinking experiment. I hope you could follow a little bit. Let me move on. Another topic I still wanted to cover is AI. It's all around. Everyone talks about it. What does it actually mean? I brought here 4 let me call it use cases, where we need to utilize AI in the best possible form. I mean, there are 2 classical ones. Utilize AI in the development of the product, in the development processes, increasing speed, increasing quality, automation of development processes, and utilize AI for the product functionality. So enhance product functionality, improve performance, improve quality of sensor data whatsoever. These are the 2 classical ones. And if you think about AI, at least in my field, everyone mentions these 2. But I think there are 2 more. And I put them on the bottom of the slide. Application engineering, that's not a classical product development. It's more, you have a product, a global scalable product, and then you need to apply, to calibrate, to configure it for a specific use case. And also here are quite some efforts. I mean, some of our products, they have more than 50,000 parameters. You need to calibrate that. So AI could be very helpful to increase even the speed of an already global scalable platform, to even increase the speed to bring it into specific use cases in vehicle applications. And the other one is improvement of product efficiency. What does it mean? I mean, of course, we need to make sure that our products are cost competitive and performance competitive. So cost efficient design. AI could help there, right? Or when it comes down to ECU efficiency, runtime, or reducing the coding complexity and so on. So it's the efficiency of the product itself. It's not enhancing a function or a performance, it's the product efficiency. So these fields I see, but I think it's important to mention that it might sound like AI is a tool that we then utilize here and there, but when you deep dive into this and how you implement it in your daily working, I realize it's not a tool. It's a transformation. And that is how we are approaching it. Why it's a transformation? Because you realize you need to change your process. You need to change the way how you document data and in which kind of formats and where you document it actually. So we need to go here for a transformation of how we develop products, and then you will get the maximum utilization of AI. And there is another aspect I want to mention here, and you see it in the subtitle. And what I learned is an AI is just as good as the data that was used to train it. So data is a crucial factor if you want really to maximize the output that you can get out of an AI. And I think you have seen our portfolio before, that with all our deep system expertise across all the vehicle domains, we have actually all this proprietary deep expertise data to fuel an AI to deliver the output that we need to increase our competitiveness. So let me conclude. So around these, what is the takeaway of today? Around these big streams, around converging technology trends and the regional diversification, I think, and I want to say here, that whatever path our customers in the different regions take, ZF can enable a fully flexible approach to it. And that will be most important for the future, for any supplier. I will not, how much time do I still have? I will not go through each of these points. I mentioned them. SDCV is evolving, but on a gradual path forward, practical implementation approach, considerate approach, step-by-step approach. AI will be fueled by software-defined architectures, and basically it's a fundament for it. Decarbonization, I already mentioned. There we need to ensure we have there multiple paths towards decarbonization, because the speed of adoption is different across the regions. And I think we tackle it in exactly the right way with the trucks and hybrid. Combined system intelligence, I showcased the example with the synergy between braking and e-drive, and that was just one example. There are many more out there. Assisted and automated driving, so advancing these high performance computing units and improve step by step the assistance and the automation. At the end, what we want to achieve and what we want to, let me say, claim is a full motion and safety intelligence enabled by the technology evolution that we are actually also fueling, and by managing the diversity. And the long-term direction is clear: zero accidents and zero emissions. So that's it from my side.